In the last part of the course, I will talk about several piezoelectric devices, their principle of operation. There are many that I will not mention, and these are somehow those that I think you should hear about. So first are surface acoustic waves devices that we have already mentioned before. I think you can find some information. Well, there are certainly many books. This figure here is from the book by Herbert, Ferroelectric Sensors and Transducers. It's a very good book. I don't know whether it is still in print, but it's useful to consult it. So what happens here? Well, the surface acoustic waves are the waves that can be excited in any solid body. They are limited, confined within a very thin layer at the surface of the material, and propagate only on the surface. So in that way, they are similar to seismic waves in the planet, in the Earth that we have. We cannot go through theory of this or anything, we don't have time, but basically this is how it looks like. You have particles that would oscillate following an elliptical path, but not move away from that, and the amplitude of these oscillations drops down very quickly as we move from the surface, and the actual wave moves in this direction, confined on the surface. In that sense, it is similar to water waves, except that the movement of the particles in liquid and the solids is different. So it's not exactly the same thing, but it is similar in a sense that particles that it is present, wave activity is present only on the surface and doesn't go very much into depth. So you see here, there is almost no movement in the depth, and here the amplitude is much smaller than on the top. So where is this used? There are many applications, and one of them is for so-called delay lines. They are widely used in communication devices. You have a piezoelectric material here, okay, and you put on the top of that material interdigital electrodes like this. Then you have a input electromagnetic signal who comes on this set of the interdigital electrodes, and causes through the piezoelectric effect a surface acoustic wave, which will propagate on the surface and come to the second set of interdigital electrodes. And on that second set of electrodes, piezoelectric acoustic signal is transformed back to electrical signal, and then that goes to a circuit, to a load. Why you want to use this? Well, this is used when you want to delay electromagnetic signal. Acoustic waves propagate with a velocity which is much smaller than the velocity of electromagnetic waves. And sometimes you have electromagnetic signal that you have to delay, to stop while something else is being processed. For example, in the TV sets, your TV set has to deal with intensity, black and white signal, and also with the color. And they are processed with two different electrical circuits, and that takes a different time. So you need to slow down one of them and then synchronize it with the other one. And these piezoelectric delay lines via surface acoustic waves are very good for that. So this is widely used in communications, in mobile telephones, and so on. And the delay time is given by a ratio between the distance between interdigital electrodes and the surface acoustic wave velocity. Surface acoustic wave velocity is different than the bulk wave velocity. They are for the wavelength is defined by the distance between ID electrodes, and this can work up to gigahertz frequencies, which require line width of interdigital electrodes to be comparable to 1 micron or even less. What you need, what are the requirements for these materials, are materials with a high coupling coefficient, which is again different than coupling coefficient of a bulk. You need a low temperature coefficient because this is used to synchronize circuits, to delay them, and so this shouldn't depend on temperature very much. You need materials that have very low losses to keep clean signal, and you need a high density material. So you cannot use ceramics. Ceramics have higher losses, they have domains, and also because you need these very fine interdigital electrodes. If you use a ceramic, the grains of the ceramic would be comparable to the distance between interdigital electrodes. So grain boundaries, different orientation of grains, and so on would all affect the propagation of surface acoustic waves and introduce a lot of acoustic losses and noise and so on. So what one uses are single crystals, lithium niobate, quartz, lithium tantalate. They are all good crystals to be used. And nowadays people are using aluminum nitride. That's one of the best materials. It has very stable properties, very low temperature coefficient, and can be made with a very high quality and decent coupling coefficient, and can be relatively easily produced. Another application that I think you should know about are so-called piezoelectric transformers. You can transform a low voltage into high or high into low voltage with piezoelectric materials using resonance, using piezoelectric resonances. What do? You first polarize material in this direction, and then put electrodes here and polarize it in this direction. So this part will be polarized like this, and this part will be polarized like that. Then you take a signal that you want to magnify, and you apply it over this part of the crystal, but with a frequency that corresponds to the resonance frequency of this whole length of the transformer. And then through the resonance, you will produce a huge amplitude in the current here that you can collect, put over some load, and get a voltage which will be dependent on that load, but in general very high. So here are examples. You can amplify 1 volt signal to 400 volts, so it's 400 multiplication on a load of 100 mega ohms, or 40 volts over 50 kilo ohms load from well, 100 from 40 to about 300 volts, so almost 10 times. The problem with this, you can also control by the load what is the width, what is the bandwidth, where you have useful amplification. Efficiency of these motors, of these transformers, is very high, something like 90%. And they have many advantages over conventional motors. First, they have a small size, millimeter to centimeter range. They are very light. They are not as heavy as electromagnetic transformers, much less heavy. They are noiseless. There are no eddy currents and magnetic fields, which cause a lot of noise in electromagnetic ones. They are unflammable. They have a very large insulation resistance and therefore relatively low power consumption. Some disadvantages is that you need impedance matching circuits. You need frequency stable circuits because they work over a limited frequency range, and output is sensitive on loading. However, if you make a transformer which is not universal but works only for a specific application, then they are great. They can be made in a very thin, something like 1 millimeter thick and a few centimeters big sizes, so you can put them in thin computers. I think that Toshiba used, I think it's Toshiba who used them for backlighting of computer screens. And they are used in many other applications where you don't want magnetic fields. For example, people in CERN, they have some sensors for particles which are very sensitive, and they needed something that is not too sensitive to magnetic fields, which they have in these accelerators, and they wanted to use piezoelectric transformers for their experiments. But otherwise in electronics, they can be used. Apple used them for, I think, iPads, also for, well, I actually don't know for which application, but Apple use them. Another application that I would like to mention to you is piezoelectric gyroscope. So how can piezoelectric material be used as a gyroscope? If you have a vibrating, if you have oscillating pendulum, okay, and if there is a rotation, then there will be a Coriolis force which is perpendicular to the plane of vibrations, of oscillation of the pendulum, and that force is proportional to the speed of initial speed of the pendulum angular velocity, and is proportional to the mass. So people have used this. If you have such a prism, and then you have a piezoelectric elements here, I will explain how it works, and then if this whole object rotates, then you will have some Coriolis forces which will force otherwise equivalent acoustic waves to behave differently. The actual gyroscopes made are having different shape, but this is the principle. You can go on the website of Murata, which is one of the largest producer of electrical components in the world, and if you type gyroscope, you will find some discussion and pictures of actual gyroscope. So how does it work? So imagine that we have this pyramid prism made of very perfect elastic materials that can be quartz glass, and then you have two types of piezoelectric transducers. One which will produce driving which is driving element and will produce driving signal, and the two others which are receptors. Now, if this one is forced into vibration, it will emit acoustic wave into this pyramid and prism, and the charge that is produced by these two identical transducers will be exactly the same. If you subtract their signals, you will get 0. Now, if there is a rotation, then there will be a Coriolis force inside, and the acoustic signal received by the two is not going to be exactly the same. So there will be some difference, and that signal will depend on the velocity of this whole setup and on the angular velocity and direction of rotation. So you can use this to navigate and to keep track of all rotations. And I think they had a Toyota car which was driving, navigating only by this piezoelectric gyroscope, and was able to make a circular road of about 300 kilometers and come navigating only by this within very close position to where it started from. Piezoelectric gyroscopes are used in helicopters, for example, where it is very important to know position, orientation with respect to the ground and so on. So a lot of that for a military, but also for civilian applications, consumer applications. Piezoelectrics are also used for high intensity transducers. Here you fabricate really high you apply very large voltages on bulk PZT elements. You need a hard PZT because you don't want much electrical or mechanical losses. You are driving them at high frequencies in a kilohertz, sometimes even megahertz range. There will be also heating through domain wall motion, so you want to minimize that, and the hard PZT is the best. Anything that is in contact with that will vibrate with a great force and amplitude, and that can be used for welding of plastics by friction. It can create a high temperature and then weld plastics. It can be used for liquid pulverization. So if you have, for example, humidifiers, you put the piezoelectric element under the surface of water and drive vigorously this piezoelectric element, and this would be enough to pulverize ceramics to produce waves, to produce little particles that will go into atmosphere surrounding it. It can be used for ultrasonic drilling. So I told you already that the Mars rover had a piezoelectric actuators used for drilling. It is using such high intensity transducers, and it is also used for ultrasonic cleaning. You put these piezoelectric elements around walls of a vessel. You have a liquid, and by driving these ultrasonic elements, you will produce high intensity waves in the water, and the energy of these waves can clean material that you put inside. And this can work, usually works at a few kilohertz, but can work into megahertz range. Of course, at a megahertz, you have problems of how to drive it, how to have a circuit which would provide enough voltage and current power. It is also used for in medicine for lithotripsy and liposuction. So this is for melting of fat in the organism and sucking it out of organism. High intensity piezoelectric transducers are also used for teeth cleaning, drilling, and also for pulverization of stones in kidneys. So there are many applications. Another application of piezoelectric materials is in smart or active systems for noise control, noise and vibration control. And piezoelectrics are very good for this. They can be controlled with electrical means and have mechanical function, and that is ideal. So let's assume that we have let's say a steel a beam here, and that you apply a force here and let it oscillate. And these oscillations would be damped with the time, and it would take a lot of time. If this is a nice elastic material, it would take a lot of time before they reduce. You can imagine situation wherever you have some construction where you have relatively thin beams which can be brought into oscillations. Those oscillations can last for a long time. Imagine, for example, these holders of solar panels for International Space Station. They are huge. They are in a surface, in a length much bigger than space station itself. And just due gravitational field, they can enter into oscillations, and this can bring the whole space station outside of equilibrium. Now, I don't know whether they're using piezoelectrics to control this, but I'm giving this as an example. Now, how you can control those vibrations? Well, you put a piezoelectric sensor at some strategic places, and as this beam bends, that will apply pressure on this sensor. And then you connect, then you put on this beam also some piezoelectric patches, piezoelectric plates, actuators, and connect this sensor with the feedback circuit with these piezoelectric plates. So if this bend, there will be a compressive forces on these actuators. And then sensors tells those actuators, because it knows that beam is under compression, to apply tension, to expand. And opposite signal on the other side. Because if this side is under compression, then this side here will be under tension. So you want to compress these and put under tension these piezoelectric elements, and that will stop this element from moving. So here is an illustration. I'm sorry, I don't have a reference, but if you look with vibration control with piezoelectrics, you will find such examples. So if you don't have a control, it will take a long time for damping in the material. However, with the control, this happens within a millisecond. You see it vibrating, and suddenly it stops vibrating, and vibrations are zero. And with a good feedback circuit, you can do this even for multimodal vibrations. So here you have two frequencies. You have this one, big one, and then you have this higher frequency movement. And once you turn the control off, the vibrations stop. It's a little bit longer takes than in the above case, but still very quickly. There is very little ringing. This works very well. There is another way to do to apply smart or active control and make smart or active systems with piezoelectrics, and that is to actively control stiffness of the material. So how can you control stiffness of the material? Imagine that we have a very stiff material put on top of a very compliant material. For example, here you have a piece of steel, and here you have a piece of rubber. And the whole sandwich, the whole composite will have a compliance of the softer material. Okay, so under pressure, this will deform, and the mechanical properties of this steel almost don't matter. Can we control the stiffness of a composite? Well, it's possible if we put piezoelectric actuator below this stiff material. And now you have two possibilities. When a force is applied, this actuator can go down. It can compress, and that will make the whole structure thinner than if actuator is not doing anything. Or you can do even the opposite thing. You can make actuator going through some active control. So you would have some active control here. Here you would have some sensor, maybe sensor you can put outside and connect it with the actuator. And you can make it even that it expands, that it goes against the force, which would make it like a negative Young modulus. So you would get very stiff or very compliant material by using two materials that are both very stiff. Piezoelectric ceramics are stiff, and this piece of steel is stiff, but by moving through the active control piezoelectric actuator, you can mimic very compliant or very stiff structure. And this has been tested to make stealth submarines. You have heard about stealth planes, the planes that cannot be detected by radars. So this is electromagnetic waves which reflect from the plane, and you can do this in many ways. Make a shape of the plane such that radar is scattered everywhere, or part of that can be absorbed in the material, in the composite material that plane is made of. Well, you can do similar thing with the submarines. You can put piezoelectric actuators into submarine walls, and then when if you have some sensors away from the submarine, it can sense signal coming from the donor, from the sonar, which wants to detect that submarine, and then the wall of the submarine can withdraw, making reflection weaker. Or it can expand in a case that you want a stiffer wall, for example, if you go to some pressure and so on. So in principle, this works. There is a way to make passive damping with piezoelectric materials. So imagine that you have a piezoelectric material on which you apply a force, and this is some kind of vibration, and piezoelectric material starts vibrating. Now, if you will have mechanical and then electrical energy, and if you can dissipate this electrical energy, that would then reduce vibrations. You make material stiffer, and you can do it by using piezoelectric shunt resistor across your piezoelectric elements. So what you do, you put piezoelectric element in vibrating structure. Structure vibrates, piezoelectric vibrates, and then you can, if you have this shunt capacitor, the part of that energy which is transformed from the mechanical energy into piezoelectric will be removed through heat, because basically you are producing current, and current will produce heat. This works. You can make very elaborate structures. Here is a system that which is induced into vibration, and then when you remove the driving signal, it takes some time before vibration die off. But if you have this control, if you can turn on different of these shunt resistors, you can kill vibrations very quickly. So there are no sensors here. There is simply a way in which you can connect these shunt resistors and disconnect. This has been used in shock absorbers in the skis and snowboards, snow skis, and in tennis rackets. When a tennis player hits hard a ball, the tennis rackets will start oscillating, and that is very hard on the hand of a tennis player, and you want to remove those oscillations as quickly as possible. So if you have a piezoelectric fibers inside, you can transform a part of that elastic energy into electrical energy and dissipate it through some resistors and remove the vibrations. Similar thing with the skis. If you are driving over uneven terrain, the skis can go into oscillations, and you want to remove this as quickly as possible. And that can apparently be done if you have piezoelectric patches inside, which would take part of that mechanical energy, transform it into electricity, and that electricity into heat. With this, I finished the course. And I would like to ask you again that inform me of any errors that you have noticed. I know that there are quite a few. Of some of them I'm aware, some of others, some of them I'm not. And I would appreciate if you can tell me where you notice the errors.